Welcome to another GC Basic video and demonstration. This is for the part 9, discussing timers and timer interrupts on the legacy chips. I will be using a 16F specifically, but the same applies to a 10F and many of the legacy 12Fs, so legacy chips. Part 9. Like and subscribe, give us a thumbs up, let the video run all the way through. Without that, the metrics don't work and Google don't even respond to a search on GC Basic. So you need to do that. Thank you. So we're going to look at timer overflows. Actually, I think we also see timer 1, 8 bits, 6-bit 16-bit timers, just to flash the LEDs. We've been using wait up to now, but you need to understand that you've got all the timer access to all the timers inside the microcontrollers. And so this is going to show you how to do that. So I've assumed we've got all these prerequisites, basic software is installed, GC Basics installed, you can program it, you've got the PIC attached, LEDs, a potentiometer, some switches, USBs, TTL still there, and you have an LCD now, because that was the last tutorial, but not critical, because I'm not a lover of LCDs. This is the board I'm using. We can look at the board. Here's the board. It's actually still running the demonstration from the previous tutorial. It's got great capabilities. LCD serial is connected. Microcontrollers here. I'm using a 40-pin. I took it at random. A 16F1937. This has got sound, EEPROM, which will be seeing all this. Potentiometers, LEDs, prototyping areas, buttons. Fantastic. Very cheap. This is what I've got connected. No change from the previous tutorial. We had the TX and the LCD, and that's what's documented on here. So let's look at timers. We need to get a bit of a primer to make sure that we understand, because this is what this change. This is different from the newer chips. Legacy chips are different, and I'm not going to explain the differences. This is the way they work on legacy chips. So you can generate very accurate time delays and time sequences. The microcontroller can have an external oscillator that will give you specific measures of time. So you can run loops, run interrupts. But whilst all this is going on, the CPU can be doing other things. So the CPU inside the microcontroller is not doing a fixed function like the wait command. A timing is nothing else, but this is just as simple as a counter. It just counts numbers using these pulses from the internal and external signals, and it just increments a register with a value. And once it reaches a maximum value, it will go back to 0. So if the range of the timer is an 8-bit value, it will go from 255 through to number 1, and when it gets to 0, it will just set a flag called the overflow flag and generates an interrupt if it's enabled. They're very simple. I thought a long time ago they were complex, but they're not. They're as simple as that. What we're going to see is how to set it up. That's the code using init timer, start timer, set timer. And we're going to see how in the tool chain that you've got a calculator to help you understand the parameters and how they actually differ from the newer chips. But also you've got this diagram I put together, and we'll walk through that diagram to sort of give you the flags of, so why do you need to have an init timer? Why do you need to have a start timer? Why do you need to have a set timer? And what else can you do? This context is very important as a primer. Because here's the diagram from the data sheet with some circles on it. And essentially it says magic happens, but it doesn't really. Let's just bring up a pen. It's saying I can have clock sources, and the clock sources are over here, okay? They're in this area here, and they get fed into particular gates, and the clock then starts to increment. And so I'm going to be using the oscillator, the internal oscillator, and I'm going to push it through into here to go to zeros and ones. I'm going to push it through what's called the prescaler, and that prescaler will help me increase the frequency. I'll show you that in detail. Then I'm going to set what that prescaler value is. It will come through, and then eventually it will run through a clock, and when the clock actually goes to zero, it will set an overflow flag over here. Let's walk through that. It looks like this. So these timers, as I said, accurate delays, and we're going to end up on the right, starting on the left, going to the right with an interrupt. So how does that all work? Well, the first thing we do, we need to select the oscillator. And typically, it's the frequency of the oscillator divided by 4. And we send it that sort of command. And that generates as a signal. And that's a fixed frequency. And that's always the same because that's linked to the oscillator. But let's assume that that's too fast. Or too slow, too fast, too fast. I need to stretch it out. How do I stretch it? How do I stretch that out? I stretch that out by changing what's called the prescaler, and I can stretch it out, which means my range is better. So what was maybe a limited time period when I'm using the oscillator, but if I can prescale it, it gets the signal frequency gets greater. I have to enable the timer. Timers are not what's called free running. They need to be told to be enabled. Once they're enabled, they then start counting. And let's assume I've set the counter in that red box in there to 100. Well, it will get a signal from the oscillator, it will go through the prescaler, and it will go from a high to a low, and then we'll increment it, and it will go 101, 102, 103, 104. It will carry on going through there until it gets to, we'll say, arbitrary number 254, 255. Now the timer zero counter is getting a little bit close to what's the important part. There's an overflow at 0. And if you notice that this changed to a 1, let's go back. It was 0 before. Only when it goes to 0 does the overflow get set. So once that gets set, we can test for that. And if I've got the interrupt enabled, and the interrupt, I get an timer overflow interrupt. So there's several things I have to set here. Clearly, I've got to set timer enable, interrupt enable. I've clearly got to set the prescaler. I had to set this timer here. That's what all the values are. And that's why we need a number of values to make that magic all happen. Let's look at some sample code, review the results. And we're going to look at 3 different types of timers. Timer 0 overflow, an 8-bit timer, and a 16-bit timer, because they are slightly different. And we're going to use 2 different types of timer. But essentially, all we're going to do is increment the LEDs from left to right and just keep up what we've been doing in the past. I've got GC code open. There it is. So let's have a look at what we're doing. Open up Explorer, Control B or top right hand corner. And I've got lots of different things in here now. I've got all my source code and all my other reports that we'll be looking at later on. Control F in there, type in GCB and set the filter. Now I can just see the source programs. We're looking at 110, 120 and 130, which is rotate the LEDs using timer overflow. Load that one, 8-bit timer and the 16-bit timer. I've loaded 3 programs. Control B to shut that down. Select the first one, which is the overflow event one, and that is 110. Let's look at the program. You've seen all this before. Specify the chip, option explicit, master clear on. No change in all the constants, nothing's changed. Nothing has changed. You can work through those, and I should, I suppose. Setting up the baud rate, which we're not using, set up some constants for the LEDs, set the LEDs as outputs, set up a constant to the potentiometer, set up some constants to the switches and set the switches as inputs, set up the baud rate, set up the LED. Oh, there's a repeat there, look. It doesn't matter if you repeat things, by the way, but I will tidy that up. Because the main program starts here. where it says start program. So the first thing we need to do is we're going to set up the interrupt. The command in GC Basic is on interrupt. There's many different types of interrupts, and we can see, and there's always typically one called timer overflow, and we've got something called blink. On interrupt, when the event timer overflow occurs, call blink. Sometimes that's called ISR. It would look like this. Interrupt service routine. Your call. I'm a bit more meaningful here. I call it blink. So whenever the overflow occurs, it's going to call blink. I'm going to initialize the timer. And it says here, init timer 0 with oscillator, which is what the oscillator is. That's what I've chosen, rather than an external oscillator. I'm using the internal. And I've given it a scalar of 0. When we saw that, we have to set the scalar, and we have many different types of scalars. For this one, I think if I look in here, let me not struggle, function key F1 to open up the help. I can have any of these here. 0, I can have 2, 4, 8, 16. These are all the prescaler values. Like, oh, where do I get all that from? Confusing. Well, we're just using an overflow. And so we're going to use 0 because we're looking for the overflow event. We'll look at how we use those scalars in a moment. Let's just get the clock running. Next command is start the timer. Now the clock is running. And it will just cycle through an 8-bit value of 255 to 0, set the overflow flag. When the overflow flag happens, it will call our blink program. Where is our blink program? Let's have a look. It says timeout +1. That means timeout. I should change that to, that's the same as this. Timeout +1. Increment the timeout. So I'm using timeout to do something. It says here that when you get to 8,000 of those, you're about a second. Okay, flash the LEDs, and it really, trust me, it doesn't really matter what's going on here. It's just that we are going to get a timeout every 8,000 interrupts. So it overflows 8,000 times, and it's going to put something on the terminal and the screen. That's surprising that I've done that, but function key F5. Let's have a look what happens. Disk cam. Just programming it. It's just completed the programming. Oh look. Oh, I remember what I did. I put a little icon on it. Look. There, look, you can just about work it out. Look, little dot, look. A little C, that's a dollar. And the LEDs are all rotating. And this is because I counted 8,000 interrupts, but I'm actually counting 8,000 overflows. So I just set the overflow up. And we'll use this overflow mechanism later on. The LCD commands basically says, get what's there, invert it, which is the not sign, and put something back. Look, it's not rocket science. If I look at the terminal, what's the terminal telling us? Oh, look, if I put up here, look, put the time on, it's every second, look. Approximately every second. Now I'm using the internal clock, so if I put my finger on here, that will actually change the time. Look at that, look. And you can actually calibrate the internal clock like that. I'm just showing you timer overflow, not the actual clock signals timer overflow, because we're going to look at something else to make that work for us. So that program is timer overflow. And what we recap, what we saw is the setup. On interrupt, a type of event called blink. Initialize the timer, select the oscillator, could be external, EXT there, if you had an external clock. Set it to scalar 0 and start the timer. So where do you find all these types of events? Well, let me just press function key F4, PICInfo. We'll look at PICInfo. Inside of here are all the interrupts. And there's one called timer 0 overflow. And what the compiler is doing, it's setting up all these bits for you automatically. It's all been pre-programmed. One of the great things that the Hugh, who wrote the compiler initially, has done, that structure, all that's automatically handled for you. So all the caching and all the restoring the environment is done automatically. And so we're going to look at different types of interrupts that are in here. Timer 1 overflow is what we're going to look at next. We were looking at timer 0 there. Let's have a look at another one. Let me zoom out. Select rotate the LEDs using an 8-bit timer. Now we're going to use timer 0 in 8-bit mode because it is an 8-bit timer. And the problem with an 8-bit timer, it doesn't give you a lot of flexibility. You can set the scaler, but it doesn't give you the range. So we're going to figure out that the range on it is quite small, but we have tools to help us, which is fantastic. So the setup on this is the same, okay? Just let me reassure you, above here is all the same, all the constants. Now I've put this in here because that's quite interesting. You can tweak the oscillator using a register called OS Tune. I'm just put that there because you can learn how to do it. So what I'm going to do is I'm going to set this very small 8-bit timer to 10 milliseconds, or as close as I can to 10 milliseconds. And then I'm going to count a number of 10 milliseconds to get me to 1 second. And I do that by saying, okay, I've got a counter, if it's equal to 100, then rotate the LEDs. So how do I set this up? It's quite hard, surely. Init the timer, same as before, the internal oscillator, and a postscript of 256. Well, where did that come? Well, if you go to your demo, if you go to your tutorials, your folders, and look inside the demonstrations, here it is. Oh, you can't see. I'll zoom in for you. Look. There you go. Look. Type in interrupts, interrupt timer solutions, interrupt timed examples, and look, there's a timer calculators. And inside of there's a load of calculators. So I'm going to do exactly the same as your build, because I was looking in the demos, interrupts and timers, interrupt timed examples, and I've unpacked that into here, look, into a folder, and I run it called timer calculator. I'll bring that on the screen for you so you can see it. Look at that, it's a little calculator. What's this? PIC16 is what I'm using. I've got it set to, why is it, oh, it's set to 16 megahertz. We'll have a look at why that's set to 16 in a minute. Let's try 32, right? Because that's the default. Timer 0, I want 10 milliseconds. I've got unit of 10 milliseconds here. I can change that to frequency here, but I want 10 milliseconds. Calculate. No answer. Look, I don't get an answer. Oh, it's brought up the help. I don't get any values because the clock is, there is no scaler that allows me to get a 10 millisecond delay. I have to slow the chip down to 16 megahertz to get a 10 millisecond delay. Look, and it says here, look, timer 0, pre-scaler of 256, load it with the value of 100. The actual interrupt is 9.984 milliseconds. These are all the registers that you could set, but let's not do that because we can do it a lot easier. Here you go. We can set it in here, much easier. We can just say, init the timer with that oscillator, scaler of on 0, 256, start the timer, and then we put the value in here of 87. Why have I put 87? Just to confuse everybody. Calculator, classic calculator. Let me just pull that in so we can see it. Hexadecimal number, 87. 135. Now, that's because of latency, I reckon. Let's give it a test and see what we've got. Let's look at the rest of the program. We'll come back to that value in a moment. It's what's called latency, and I'll explain. So our program sets that value, starts the timer, and then it's running. And then what we can do, we can wait in our program until the event occurs. Wait until that overflow flag is set. Now, how did I know that overflow flag? Remember back in, I can look at PICInfo, I can say, oh right, timer 0 overflow, that's the overflow flag. If you look at the top, it says the enable bit, you don't need to play with that, but you can test for this. Brilliant. So I've tested here, I said wait a while, I've cleared the flag because you do need to clear it, and then I've reset the timer so it starts clicking again. Now, function key F5, so it counts 100 of those, and then it's at 1 second, and it goes around. I would imagine I've chosen 87 because of empirical testing. I've tested this, and what do I mean by that is, we'll have a look at the terminal to see what's happening. This is the terminal, clear that down. I have programmed it. Yeah, I'm still using the internal clock and it's not accurate enough. Like, if I did this on a 31 hertz kilohertz clock, it would be very accurate, but it's approximately 1 second. Look. And I was playing, I think that 87 was okay when it was a bit warmer in here. This is a operational principle here. The theoretical value of that should actually be 100. So let's put it to 100. You know, we should do it in decimal, really. Let's just do it in decimal because that would be a lot clearer. Program that. And why I'm using the terminal here, because it's got a little timer on it, see? I can see the time on it. Clear that down, let it program. Now it's reprogramming it. Oh, that is much. Look at that. That's pretty close for an internal clock. That's pretty good. So, what did I use? I used the init timer. I got the value of the calculations using one of the calculators. There's many up there, by the way. Started the timer, set the timer to 100. Great, we're running, and we can see the results. So, how do I get around this problem of getting bigger times on these legacy chips? I mean, this is counting up, 100 of these so I can make a second. It is hard, and that's what is difference between these legacy chips and the newer chips. They have a postscript. They have a post scaler as well as a pre-scaler, so you can stretch the clock further. We cannot do that on these. We only have one scaler to use. But what we can do, we can change the timer. We can change the timer to timer 1, and that's got a 16-bit timer. It just means the number's a lot bigger. And so in here, I will show you the calculations. We're going to init the timer 1. Start timer 1 and set timer 1. And I've used a calculator to give me the value of 306. And we'll look at that value in a moment, what it's going to do for us. If I press function key F5 and program it, it's going to send out a little dot. It's going to send a dot out to the terminal so we can see the rotation code working. Clear. Oops, sorry. Clear that down. So that's also every second. Let's see how the code works. In here, it says do loop, wait for the timer 1 flag, make it very clear, go back into here, into the previous program. That's timer 0 because it's TMR0 interrupt flag. This is timer TMR1 interrupt flag. If it's set to 0, we know it hasn't overflowed. But we haven't got that big counter in here. Look, the counter is not the same. It's actually, I don't have to count to 100 of them because the timer allows me to do that. How have I got that value then? Let's have a look. I've used another one called Mr. E, whatever that is, into our timer, into my folder. Is that it? Yeah, here it is. Different calculator. Timer calc. This one here, let's have a zoom in on that. Just shuffle things around so you can see it all. Right, I'm running at, what frequency am I running at? Whoa, I'm running at 2 megahertz. That's slow. Never mind, let's do it. 2 megahertz, 16-bit, and I couldn't have used this calculator because I can't work out how it works. That's not the one I've used. Oh, this is the one I've used here, look. Right, 2 megahertz. The frequency I want, 1,000 milliseconds. It's calculated it, and it says down here 16-bit time of results down here. I've taken I've taken this one, have I? Let's have a look in my program. It's a value of 3036. Oh, I took this one. Here we go. So I must have selected the. So here's my value. I can use the prescaler of 1.8, and it will give me a very low accuracy error rate. So that's fine. That's my preload value. My prescaler is 8. So let's have a look at my source code. Init timer 1, internal oscillator, scale of 8 with a value of 3036. That's where it got the timing from. That's why the terminal is showing us an interrupt every second. I don't have to carry the overhead of counting up 100 of anything because it's got a lot larger range. All this is documented in the help. If you press function key F1, init timer, you'll get taken into the instruction set for init timer and all its scalar values. You could also do it by hand. You can hand crank it to set the registers. You have to use one of these tools, and you can just hand crank it if you wish. So let's go back to PowerPoint and call this a day because it's a big video. What I wanted to show you is using timers, overflows, 8 bits and 16-bit timers to flash the LEDs. I think I've done that quite well. It's a big subject, big video. And next, EEPROM. Enjoy.